In this 10th lecture on Fourier series, today we shall discuss the Fourier analysis of common wavefronts. That is a wavefront. If we consider a wavefront, then the variable argument is not x but it is time t, and it generally extends from 0 to t. And if we come to the this is the variable, and then the delta is t, and the factor, the argument of sine and cosine function is 2n pi t by capital T. Now this is equal to, as omega t is equal to 2 pi, so 2 pi by t, so 2 pi by t is equal to omega, so this 2 pi and t can be written as omega, and it can be written as n omega t. So for a time series analysis, the Fourier expansion becomes like this. If we have a function f of t which satisfies Dirichlet's condition, then it can be written as a0 plus n is equal to 1 to infinity a n cos of n omega t plus bn sine of n omega t, and n is equal to 1 is called the fundamental, and n is equal to 2 onwards are called the harmonics. N is equal to 2 is the first harmonic, n is equal to 3 is the second harmonic, and so on and so forth. And the evaluation of the constant is as usual, as we have done in the case of space variable. A0 is equal to 2 by delta is equal to t 0 to t f of t dt. An is equal to 2 by t and bn is equal to and if we want to analyze the common wavefront, the general procedure is same as we have done for space variable. Let me say once again, we first draw the graph of the function in the original interval together with its periodic extension. Then we first look whether the graph is the function is even or odd, or that has have any definite parity. If so, then the calculation simply gets simplified. If there is no definite parity, then we look at the first derivative of the graph and whether there is any discontinuity in the function itself or in its derivatives. That will determine the independence of the Fourier coefficients. Then we shall calculate the relevant Fourier coefficients. Let us first start with square wave, and I am showing how to. The square wave is defined as f of t is equal to h for so the function has a height h in the first half of the period and is 0 in the second half. So first thing is to draw the graph. These are the point t by 2, t, 3t by 2. If we draw the derivative of it, the derivative of the function is 0 all alone. So what we expect? Since function has a discontinuity, Gibbs phenomena will be there, Gibbs phenomena will be there. Will be there, plus the factor that an or bn will have 1 by n dependence. This is because the function has the first discontinuity. The function itself has a discontinuity and the first derivative is continuous, so there will be no more higher n dependence. The actual calculation leads to that a0 is equal to h, an is equal to 0 and bn is equal to 2h by 5. So we can write the series. I am not going to this. Only thing that as the function is discontinuous, 1 by n dependence is obtained in B. And since the function does not have any definite parity, we are to calculate both an's and bn's. As the second example, we shall consider triangular wave. I am drawing the triangular wave case here so as to make a comparison or triangular wave is defined as f of t is equal to at in the first half and the second half. Here some modification will be required in equal to sign. Let us draw the graph of the function. This is t-axis, this is f of t-axis. In the first half, the graph increases linearly, and then in second half it goes to 0. So this is t by 2, this is t, this is 0, and again they are the triangles. This is 2t and 3t by 2. That's why it is the triangular wave. So notice that the function is continuous at t by 2 as well as this. So we write equal to sign. So be careful in putting equal to sign in the definition of the function. This point I haven't considered earlier, and it is done deliberately. So whenever you are defining a function which is continuous at an end, at one of the terminals, then do not forget to put equal to sign. As for example, if we consider f of x is equal to x square in the range x less than c greater than minus c. Earlier we have written in this fashion, but it should be actually this. This augmentation has to be done in all the previous lectures. In the study material, these corrections are there, but I haven't pointed out this yet. Now, if we plot the first derivative of the function, you see that in the first half it is a, and in the second half it is minus a. So this is the form. So what we expect? Well, no Gibbs phenomena. Since the function is continuous, no Gibbs phenomena, there is a discontinuity in the first derivative of the function. So an or bn, whichever persists, will have a 1 by n square variation, and due to this n square variation, the Sn, the partial sum, will have a faster rate of convergence. That is to say, if we go on adding number of terms, the accuracy will be obtained with smaller number of terms in this case, and but in this case a larger number of terms will be required by the, as the variation is 1 by n. So the if we go on adding the terms 1 by n, due to the factor 1 by n, it will have a slower rate of convergence and it will have a faster rate of convergence. Actual calculation gives a0 is equal to at by 2, an is equal to minus 4a by omega pi. It can become written in terms of t beta. So this is the sum. Now we come to the third waveform. Again, I want to remind you again that this greater than or less than equal to sign has been introduced here. Equal to sign arises only when the function is continuous at the point under consideration. If the function be continuous here, then you should put equal to sign. If not, then put less than sign. If the function be continuous here, then you put less than equal to sign. Otherwise you put less than sign. If we have the less than sign here, then it will also be there because they are the same points. Now come to the third option, that is the Sawtooth wave. The sawtooths are used for making regular pieces of woods in timber plants. The function is defined as f of t is equal to at for both range t less. As the graph, if we draw the graph, we will find that the function has discontinuities. This is t, this is 2t, 0. This is function f of t. So the function has a discontinuity. If we make the derivative, this is all along a. So what we expect? We expect that an Gibbs phenomena will be there because the function is discontinuous. Gibbs will be there, and whatever exists, an or bn will have 1 by n dependence and slower rate of convergence, slow convergence. So if we explicit calculation shows that a0 is equal to at, an is equal to 0, and bn is equal to minus 2 by n omega. 1 point an 0, but a0 is not 0, so we cannot say that the function is odd. If an's are 0 together with a0 is 0, then the function may be a odd one. In the case of square wave, we also found that an is 0, but a0 was there. a0 was non-zero value. And one thing I have forgotten, for triangular wave, a0 was given. For triangular wave, at by 2, an was written minus 4a by pi omega 1 by n square for n is equal to odd, and 0 for n is equal to even. That much I wrote, but I forgot to write bn is equal to 0. This is because of the fact that when we write triangular wave, it is, if we go to the negative side, it is an even function, so it is an even, so bn is 0. But here we cannot draw such conclusion. Now I come to the modified Sawtooth wave. Here the function is defined as this. So first thing is the graph of it. Graph is this. So this is t by 2, t, 3t by 2, 0. So the function itself has discontinuity, and if we make derivatives of it, it is a, then 0, then a, then 0. This is t by 2, t, 3t by 2, 2t, 0. So here we see that the function as well as its first derivative is discontinuous, but the second derivative, if you go to the second derivative is a continuous one, because the second onward derivatives are 0. So we expect that Gibbs phenomena will be there. Gibbs phenomena will be there. Plus an or bn, whichever exists, will have the form 1 by n form will be there because of this, and as well as 1 by n square form will be there from this. Now this is the plan. If we do the partial sum will show Gibbs phenomena. If we evaluate the coefficient, either an or bn, one will have this dependence, other one will be this dependence. In general, the form may be of line. They may vary as something c times a n plus, this may a plus bn plus cn square by d. This should be the most general form. In general, this a is not present, so other things will be there. Now the explicit calculation is that a0 is at by 4. Obviously, the average value of this one will be higher than this, and since the second part is half, so this, you see that this is the average value. Then an even and bn a upon omega plus 1 by n for n is equal to odd, and is equal to minus 1 by n for n is equal to even. So whatever we argued physically is correct. Bn has this part and this 1 by n dependence, and an has 1 by n square dependence. Now we come to the other two forms of waveforms. Other two waveforms, that is half wave and full wave waveforms. In electronics, it is a common to have half wave and full wave rectifiers. If we analyze the outputs of such rectifying devices, what will be the Fourier analysis of the corresponding ones? We are going to do this. Fine. Half wave rectifier. We define f of t as, first half it is sine omega t and 0 in the second half, and this is let us first draw the graph. T by 2 t, 3t by 2 2t. t-axis. This is the graph. So graph is continuous, so we should put equal to sign. If we differentiate this, we will have cos curve. T by 2. So in this part, the graph, the derivatives are 0, no doubt of it. And if we differentiate it, it will have omega cos omega t, and cos omega is plus 1 at t is equal to 0 and is minus 1 at t is equal to t by capital T by 2. So the form of the graph will be and similar here. This is the graph. So we expect that there will be no Gibbs phenomena and the expansion coefficient will have 1 by n square dependence. So we found A0 is equal to 2a by pi. An is equal to a by pi 1 upon n square minus 1 for n is equal to even and is 0 for n is equal to odd, and Bn only the first term will be there, the fundamental, nothing else. This delta function, only B1 is there, no other terms. The last wavefront that of this category that I am going to discuss is the full wave rectifier. Here the function is defined as this. I shall first draw the graph, then augment this part. T by 2, T, 3t by 2. In the first half, the sine function is this. In the second half, the sine function was there, but due to this negative sign, it is so the function is continuous all along. Basically, it is this function is mod of sine omega t function. And if we draw the derivatives. This is plus 1, this is minus 1. So we expect what we expect, that there is no Gibbs phenomena, and A and Bn will have 1 by n squared dependence. A0 comes out to be 4A by pi, just the double of the half wave case. Because here the first, every alternate half was 0, but the alternative halves are identical to the previous one. And we see that the function is an even function. If we extend this, we will have even function. So Bn will be 0 and An will be minus 4A omega pi. So the result here, what we have obtained is, as expected, Bn is 0 as f of t is even. Here the function was not even. You look at in this half, the function was this. So this is not the even function. So that's all about the analysis of common wave fronts. You do calculate the coefficient by yourself and see whether they matches with the result that I have quoted.